Represent relationships. Now, how many of you are completely unfamiliar with the concept of a tree? I don't mean the growing up kind of tree. I mean okay, so you guys are all very familiar, which is expected because nowadays we see it everywhere. You look at your folders and a folder structure, that's a tree structure. We use trees to represent relationships. So in a linear list, we have relationships too. There's an item here, and the relationship is before and after, or next to, left or right. That's it. With trees, we get a more complex relationship, which is the descendant and ancestor. Trees are hierarchical. A parent-child relationship exists between nodes in the tree. So we have ancestors, everything from a particular spot all the way up, and we have descendant, which is from a particular spot all the way down. We generally think of this as up-down for trees. Family tree gets the same idea. That's where we get the same idea. Again, the parent-child relationship, ancestor-descendant. Each of the pieces in the tree is called a node. And then the nodes, or the edges connecting them, are just called edges. So nodes and edges. Obviously, a pretty simple example is this. This is an example where I have nodes, the circles, and edges, which are the lines. This is an example of a tree. In case you're wondering, we call it a tree because it's an upside down tree. This is the root, and then it goes down here. Do you know what these are called? Leaves. These are called leaves. So it's an upside down tree. Interesting thing about trees is, here's my root. My root is at the top of my tree, but if I just ignore this stuff, what do I have left? Well, branch, but it's actually another tree. It's a subtree, but it still meets the definition of tree. So trees are defined as in terms of subtrees, or trees inside of trees inside trees, and that sounds like what? Recursion. So everything you do with trees is recursion, almost everything. There are ways to avoid it, but it's painful. So trees are inherently recursive because they have this kind of hierarchical structure where these are subtrees of this, which is a subtree of this, and so on. A subtree in a tree is any node in the tree together with all of its descendants. So if I was to draw my original tree back here, then I have the whole tree, then I have a subtree from here, I have a subtree from here, I have a subtree from here, actually just a single node. And a subtree. So this node. So I have, well, that's the definition of subtree. So I have a picture that's the same as what I drew. This maybe is prettier. I don't think so. But we have a tree here with nodes A, B, C, D, E, F. And then here's the subtree out of that tree. Start with B, so B, D, E, F. And again, I'll restate, notice that this subtree is actually a tree. So subtree just means it actually has a root. The root of your subtree actually has a parent. All right, here's an example where we might run into this in real life, because we do run into this in real life, both in using computers, as well as non-computer things, as well as concepts, which we'll talk about in a little bit here. This looks like an org chart from a company, right? You have some president, and then the VPs and the directors and so on. So everyone who has a job probably works in a place like this. I've heard of very few places that don't have a hierarchical org chart. Even if they pretend they don't, there's still someone in charge. I mean, my cats at home have a hierarchy. I have 4 cats. And there's a distinct hierarchy of who the boss is and who's not the boss. And
where do you fall?
I'm the boss, actually. It is interesting. Our cats are like dogs. I mean, you can call them and they will come jump up in your lap. You can tell them to go to their room. They will go to their room.
Mine's like that too.
And,
He sits and he lays down.
Yeah.
And he potties in the toilet.
Well, ours doesn't do that. But sidetrack, of course. But our cats will lay down on their back, put their arms up, they want you to rub their tummy.
Mm-hmm.
So
That's
they're
awesome.
dogs.
Dog
they
cats
just
are the
aren't as
best.
smelly and messy.
Yeah.
Okay, so then we have a family tree here. I assume you guys recognize that family tree. Simpsons, yeah. Okay. Mark's not the parent. No, these are the grandparents, right? Yeah. I didn't know about these things.
I don't know about Mona.
And I guess no parents, right?
I think it was confirmed. Like somewhere around the whatever,
Yeah.
hundreds of episodes. There's got to be one, right?
Yeah. Okay, so kinds of trees. A general tree is, this is kind of the mathy definition for a tree. A set T of one or more nodes, so you have to have at least one node. Actually, you can have an empty tree. But a set of one or more nodes such that T is partitioned into disjoint subsets. So T is a set of nodes, and the two subsets, or where you have a single node, which we call the root, and then the other subsets are all general trees, which are subtrees of the root R. So this is a fancy way of saying the definition of a tree is a root, and then all the subtrees below the root. And then, of course, each of those are defined as their own root with their own subtrees. So it's a recursive definition. That's just the general tree. An n-ary tree, n is meant to be like a number, but we'll say n-ary tree. An n-ary tree is a set of T nodes that is either empty or partitioned into subsets where you have a single node and possibly, or n, up to n subsets or subtrees of R. Again, this is a fancy way of saying that we have a root with as at most n children. So, binary tree would be two-nary binary tree. A binary tree then is a set of T nodes with most two children. And generally, we call those children the left and the right. And it should be obvious which is which. So you have the left and the right subtrees. Now, some of you may have heard of binary trees or binary search trees. Binary search trees and binary trees are not the same thing. A binary search tree is a subset, the more specialized version of a binary tree, but we'll get to that in a bit. Okay, so we got this down, right? Here are some examples. These are all binary trees, and you know that because for each node there's at most two children. This is showing how we can use binary trees to express algebraic expressions. So A minus B, we put the operator here at the root, and then the children are the operands. This is a little bit more complex, A minus B over C. And again, we have this here, but we have minus for the operator, A for the first operand, and then the second operand is actually the result of another operation, which is another binary tree. Same. Probably not go over that again. This idea, using trees to parse expressions, is something you run into in compilers, those of you going on BSU, all that stuff. And then in computer science people, you'll run into a compiler class at some point, and you'll need to build these. So, that's binary tree. The only thing about binary tree is it has, for the root, it has at most two children. It can have zero, that's okay. In fact, leaves have zero children, that's why they're leaves. But otherwise, there's nothing else required. A binary search tree is a binary tree, so for each node n in a binary search tree, it doesn't say, but it's a binary tree where n's value is greater than all the values on the left, in the left subtree, and is less than all the values on the right subtree. And this is with no duplicates. If you allow duplicates, then you have to decide one side or the other accepts the equal. But with no duplicates, everything on the left is less than the node itself, and everything on the right is greater. So here's a picture of that. Now I'll come back to more formal definition in a second. But here is a picture just using names, alphabetized, of course. So my root is Jane, and you'll notice that all this subtree, Alan, Bob, and Ellen, are all less than Jane, alphabetically, not like the value of their person, just alphabetically. So Alan, Bob, Ellen, less than Jane. Nancy, Tom, Wendy, they're all greater than Jane. Now, if you notice, these are proper subtrees that are following the binary search tree principle. So if I look at Bob, again, I have Alan and Ellen honoring that same rule. Alan is less than Bob is less than Ellen. And then this follows the same pattern. So that same constraint applies throughout the whole tree. When you have that, then we call this a binary search tree. So going back through this definition, in, for each node in, all of them, in the binary search tree, also called a BST. So for each node in a BST, n's value is greater than everything in subtree L, or the left subtree. N's value is less than everything in subtree R. And then both of them, both the subtrees are binary search trees. Oops, that's what we have here. Yes?
So what happens like if you were to put in like the name Aaron, like AARO? Where would the AA go into that list? Because it's
Sure. So that's a good question. We're certainly gonna talk about how we insert, but let me just answer how we do that now. So Aaron, AARON, is less than Jane, right? Less than Bob, less than Alan. So you would end up adding another node right here.
I was trying to think of something that would be in between Bob and Alan. I was thinking it that way, but just because it seems like.
Well, so between Bob and Alan might be someone who's
Andrew.
Azalea.
Yeah.
That's a nice girl's name, right? Azalea. AZ.
Yeah.
So AZ is greater than Bob, less than Alan. So greater than Bob, it goes here. It's less than Alan. I mean greater than Alan, sorry. Greater than Alan. Where did the greater than Alan go? It would go right here. So we'd have the node here sticking out with this.
Okay. I was trying to envision how that
Right.
worked with, okay, that makes sense. Thank you.
Okay. Some more terminology now. As I said, it's kind of sprinkled in here. It's the height of a tree. Definition of level, so we've got two things here, height and level. The definition of level of a node n is if n is the root of the tree, then it's at level 1. Otherwise, in the level of the node is the level of its parent plus 1. Again, keeping up with the idea of a recursive definition for this stuff. One of the things that confuses me all the time, and I'll try and cut that off for you guys so you don't get confused. For some reason, right, in computer science, we always start counting at 0, not levels. It says level 1, 2, 3, 4. We don't start counting at level 0. Unless you want to call the empty tree level 0. But we don't, in this case, I always get us off by 1 because of this problem. First level, 1, 2, 3, 4. So if the n is the root, it's at level 1. If it's not the root, the level for a node is the level of its parent plus 1. Make sense? So the height of the tree, in terms of levels, if t is empty, the height is 0. Otherwise, if t is not empty, the height is equal to the maximum level. So in this case, my tree here, what's the maximum level? 4. So the height of this tree is 4.